Previously, we looked at strings and standing waves on strings, and remember they're caused by wave energy moving back and forth between the two boundaries and interfering with themselves, really. So in other words, a wave travels this way, reflects, comes back, and when it reflects with itself, this could happen with any two waves passing that have the same frequency. You can have this weird pattern that ends up looking like, well, these. And we talked about different harmonics. The first harmonic, the second harmonic, and the third harmonic. Okay, so the first harmonic might have a certain frequency. The second harmonic would have 2 times that frequency. So really F2 equals 2F1. F3 equals 3F1, etc. So those harmonics are very predictable. All we have to do is know, okay, visualize. These are nodes. Nodes have to be at the ends for fixed ends of a string. Okay? And they have to occur at the ends there. So we can't have, for example, on a string like this, we can't have something that looks like that because the string can't vibrate back and forth there. So the only energies that resonate on that length string are going to have, I should say the only frequencies, the only wavelengths that are going to resonate are going to have nodes there and there. And that means it's a multiple of a half wavelength because it's always 1/2 wavelength between adjacent nodes. So there's the longest wavelength, the lowest frequency that could set up is going to look like that. We call that the fundamental or the first harmonic. The second harmonic is going to be one where it's one entire wavelength. 2 half wavelengths fit. Here, 3 half wavelengths. Now what we want to talk about is longitudinal waves in a pipe or a tube. And I'm going to start off with what's called open ends, both open ends. So we're going to be talking about tubes or pipes. And wind instruments are based on this concept. If they're open at both ends, there's really 2 different schools of thought. When we're drawing this, that's that's transverse, right? Longitudinal doesn't look like that. So if we're looking at drawing a standing wave in a tube, there's 2 ways of looking at it. One is displacement. And these things can move freely back and forth. So this would be a displacement antinode at each end. Or you could look at it as the pressure. And the pressure doesn't really change. It's just the atmospheric pressure outside. So you could look at it as a pressure node. Okay, it's a little harder to visualize. Well, you'll see in different textbooks, you'll see different things where they consider the open end there to be a node or they consider it to be an antinode. Okay. Almost doesn't matter what you do because all we're really concerned about is the geometries of this thing. In this class, I'm going to consider it to be an antinode, so we'll be talking really about the displacement. So let's take a look at that. So if there's an antinode there, and there's an antinode here, and the antinode is the part that can move the most, right? So really we're looking at the part of the wave that is at the end would be like that, and the part of the wave that it's the end here would be like that. Again, looking at 2 displacement antinodes. Well, the longest wavelength that can fit in there, let's just draw a big standing wave, okay? Again, this is transverse, but it could also be the graph of a longitudinal wave. If I take an antinode, let's just take that antinode. The longest possible wavelength that could fit in there is one that only has, again, 1/2 a wavelength. So it's the next adjacent antinode. That means the wavelength in here looks like this. Okay. That's the longest wavelength that can resonate in an open tube. Now, if we keep going down, let's look at the next one. And by the way, that's a quarter wavelength. That's a quarter wavelength. This is a half wavelength. It's a half wavelength between antinodes. Okay, let's look at the next one down. So that would be the first harmonic. The next harmonic would be from one antinode to the second antinode down the road. So it would look like that. And that's honestly how I recommend you draw standing waves in tubes. Open ends, real easy for reasons you're going to see. If one end is closed, it's really tricky. Okay, so there is the next harmonic up. And in fact, since the wavelength is 1/2 of this wavelength, look at it, that's a half wavelength is equal to L. Let me do that. Just looking at the geometry. 1/2 wavelength equals L, so the wavelength is 2L. So that's the longest wavelength that will resonate with that tube. This one, there's a half wavelength, there's a half wavelength. So it's really 2 half wavelengths equals L, lambda equals L. Well, the speed of sound is really what we're talking about with this when we're talking about longitudinal waves in a tube. So if the wavelength is half as big, the frequency is twice as big. So just like in this case, the second harmonic had twice as high a frequency. Similarly, the second harmonic here, F2, is twice that frequency. And we can keep going down here. The third one, again, here's the skill of drawing it. Draw just a random standing wave and say, okay, we've got an antinode over here, so let me start there. And I know the next one is going to be, okay, there's the first. That would be like that, if it just looked like that stretched out. That would be the second. That would be the third. So I'm going to try to draw that in there, and it's not that easy. Like that. And we've got 1/2, 2 halves, 3 halves. So 3 half wavelengths is equal to L. So lambda is equal to 2/3 L. Okay. So at any rate, when we go down this list, all these wavelengths, all these harmonics exist. The first and the second and the third and the fourth and the fifth and all that business, right? So it's very much like this, just kind of flipped. Instead of nodes at the end, we have antinodes at the end. Okay, now we can do all the geometry. So very important to be able to draw these waves, to be able to figure out how many wavelengths fit in this tube of L. And we can use the speed of sound and the wavelength to figure out the frequency. Now, we're going to do a harder one, and that is closed at one end. And closed at one end can be really confusing for a lot of people. If it's closed at one end, there's some different things that happen, okay? So first of all, let's look at closed at one end. This is going to be an antinode. This is going to be a node. So the longest wavelength, again, let's draw our wave like this. The longest wavelength, if that is where that node is, the longest wavelength is going to be a tube that ends here. So think of drawing that stretched out, the next antinode, the closest antinode. So there's your fundamental. Notice that that is 1/4 of a wavelength is equal to the length of the tube. So that's how you set up the relationship between the wavelength and the tube length, or the pipe length. Now, you would think the next one up would be the second harmonic. Oh, okay, let's just make that tube, let's just go 1 more quarter wavelength. But that's a node. We got to go to the next antinode. So the next harmonic that exists is really the third harmonic. It's 3 multiples of this first one. Okay? You see why? Because we can't go to the next node. We've got to go to the next antinode. Antinode has to exist at this point. So there is no real second harmonic. Okay, let me do it this way. Let me draw this. So the second harmonic would look like that, but it does not exist because that's not an antinode there. So we come up here and we draw like this, and there's your third harmonic. So even harmonics don't exist. Only odd harmonics exist. Even harmonics can't form. Okay? So let's look at this. Well, so if that length is lambda over 4, this length is going to have 1, 2, 3 quarter wavelengths in there. So the lambda would be 4/3 L. This lambda would be 4L. So you can see the wavelength decreases by a factor of 3. The frequency increases by a factor of 3. So we can still use that relationship between the fundamental frequency and the higher frequencies, but there will only be odd multiples, odd harmonics. So we won't have these even harmonics in there. So how do you solve problems with this? First thing is to draw it. If you know what harmonic it is, draw. And again, these are multiples of quarter wavelengths if you have a closed end, right? So if I wanted the first harmonic, I would start here and go to the first antinode, right? So I'd go 1/4 wavelength, and that's how, if I erased it there, that's what my wave looks like, my standing wave looks like. If I go to the 2/4 wavelength, that'd be my second harmonic, doesn't exist. Third harmonic, right? If I had to go to the 7th harmonic, 1, 2, 3, 4, 5, 6, 7th harmonic would look like that. And if you draw my pipe like that, that's what a 7th harmonic would look like. It has 1, 2, 3, 4, 5, 6, 7 quarter wavelengths is equal to that length. Okay? So that's how you geometrically deal with the types of waves that can set up in pipes. You still have the V equals F lambda relationship. You still have the higher harmonic frequencies are multiples of the fundamental frequency.